Welcome to our materials science lecture on failure and mechanical properties. In this session, we will delve into the fascinating world of how materials fail and the mechanical properties that influence their behavior. By the end of this class, you will be able to explain why materials can fail below their yield strength due to various factors such as flaws, design, environment, operating conditions, and specimen history. Additionally, you will learn to relate failure types to both macroscopic and microscopic fracture appearances. Let's explore the differences between ductile and brittle failure using the example of pipes. Ductile failure results in one piece with large deformation and significant plastic deformation, while brittle failure leads to many pieces with small deformations and minimal plastic deformation. Examining the appearance of fractures, ductile fractures are usually desirable as they show warning before failure, whereas brittle fractures occur suddenly without warning. The fracture behavior varies from very ductile to brittle. On a microscopic level, ductile failure involves necking, void nucleation, void growth, and shearing at the surface, leading to fracture. Particles act as void nucleation sites, playing a crucial role in the failure process. Brittle fracture surfaces are flat or faceted with little plastic deformation, indicating low ductility. Key features include chevron marks, intergranular grain boundaries, and transgranular cracks across grains. Flaws in materials act as stress concentrators, making the size and shape of the flaw critical. Failure often results from crack propagation initiated at these stress concentrators. The Griffith crack theory explains how stress concentration factors influence crack propagation. The radius of curvature, crack length, and applied stress determine the stress at the crack tip, leading to material failure. In engineering fracture design, avoiding sharp corners is crucial. The stress concentration factor, Kt, plays a significant role in determining the likelihood of failure. Comparing designs, we see how sharper fillet radii can reduce the risk of crashes. Designing to prevent crack growth involves understanding the crack growth condition and the critical crack length. The maximum allowable stress and design stress dictate whether a material will fracture or remain intact. Let's test your understanding with a couple of questions. In a transgranular fracture, does the fracture surface travel across grain boundaries? And, how does a Griffith crack amplify stress at the crack tip? Here are the answers to the inquiry questions. The fracture surface in a transgranular fracture cuts across grain boundaries. A Griffith crack amplifies stress at the crack tip due to stress concentration. To recap, we have covered the learning objectives, explaining why materials fail below their yield strength and relating failure types to fracture appearances. We hope this session has been informative and engaging. Thank you for watching. Please like, share, and subscribe to this channel. We encourage you to add a comment below the video for the benefit of other viewers. What did you learn from the video? What topic would you like to explore further? This presentation contains copyrighted material used under the Fair Use Doctrine for educational, commentary, and research purposes. All rights belong to their respective copyright holders. Links are provided in the video description to relevant resources.